Hey, I'm Mr. Reader, and guess what we're going to talk about? Well, I'm a math teacher, so we're going to talk about numbers. Literally, actually. We're going to talk about the number systems. And you're thinking, number systems, why do we have number systems? Well, there's different categories of numbers, just like there's different categories of, I don't know, all kinds of things, animals, all kinds of stuff. So there's different categories of numbers. So here's my recommendation. On the notes you're going to take, you need to write this down. On the notes that you take, instead of using your piece of paper this way, turn it that way. This is just a recommendation, but I highly recommend you do it. That's the way I'm going to be doing it here on this board, because we're going to probably fill up one entire side with just this fantastically beautiful chart of the different number systems, and then on the other side you can write down definitions for those things. So here goes. We're going to start with the most basic and fundamental of all the number systems, and it is natural numbers. Natural numbers. Okay, well, you're probably thinking, what are natural numbers? I'm glad you asked what natural numbers are. That looks like N-A-T-A. It's N-A-T-U. Sorry, handwriting's terrible. Natural numbers are numbers that you learned on Sesame Street. Like this episode is brought to you by the letter J. And the number 5. They never threw in negative numbers or fractions or anything like that. They're regular counting numbers. It starts with 1. It's a Linkin Park song. It starts with one thing. I don't know why. It doesn't even matter how hard you try. Anyway, 1, 2, 3, da 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 da. There you go. Keeps on going. No surprise there. Those are natural numbers. You learned them in kindergarten. Well, there once was a man that invented a number. And when I tell you this, you're going to think, well, first of all, that's just really ridiculous. And second of all, how can you invent that number? But let's talk about it. Whole numbers come next. And this individual, I believe his name was Brahmagupta, invented, that was his last name, invented the number 0. Why would you invent 0? Well, because we realized that, if I'm going to count things, it might be possible that I have none of something. And also, we needed 0 as a placeholder for other things, like for a number like 503. Well, you can't just leave the 0 out, otherwise it's 53. So anyway, this very intelligent individual invented the number 0, and it is a whole number. Now, if you're kind of lost on memorizing that, a whole number makes a O with your mouth, so whole 0. That was really awkward, but there it was. Whole number is 0. And whole numbers also include natural numbers. So we're going to put a little box around the whole thing, so whole thing, get it? So whole numbers include 0 and 1 and 2 and 3, and it keeps on going. Okay? So if I say, is 2 a whole number? Well, yes, it is. Not only is 2 a whole number, 2 is a natural number. Okay, well then we get a little bit further into this, and we get into what we call integers. We use that word a lot in math class. Integers are numbers that are whole, and therefore inherently are natural numbers. And they're also negative in the same kind of structure as these. So numbers like -2, -1, 0, 1, 2, 3, 4, -3, -4, all that stuff. There it is. Those are integers. Okay, well, now it gets kind of interesting. Because up to this point, all we've talked about are numbers that we can count that are whole numbers or negative whole or natural numbers. What if I have half of a pancake? How do I count that? Well, that's not an integer, that's not a whole number, it's not a natural number, obviously. And so then we get into things like a rational number, a rational number. Rational, what in the world was I trying to spell? Rational, national? I don't know. A rational number. The oversimplified definition of a rational number is a fraction. But it's not quite that easy. So later on, when you have to come up with definitions for these, don't just say a rational number is a fraction. Not technically correct, but we're going to go with that as a working definition for now. So a rational number could be any of those. So I'm going to start pulling random numbers out, and I'm going to give you examples of rational numbers. And then we're going to start talking about what rational numbers are not. Okay, so rational numbers are things like, well, -2 is a rational number. 0 is a rational number. 1 is a rational number. Let's see, half, it's a rational number. -5/3, it's a rational number. Yeah, that's rational. Those are rational. That's great. And rational numbers contain integers. They contain whole numbers. They contain natural numbers inherently. And they also include fractions. Now, I say that carefully because not every fraction is a rational number. Let me give you an example of a number that is not rational. That would be known as an irrational number. So let's keep the box over those. And we're going to come over here and we're going to make another category. And this category is going to be irrational numbers. Irrational numbers. And irrational numbers are, this is an oversimplified definition as well, these are numbers that aren't rational. Well, duh. So here's an example. Pi. Pi is not a rational number. Well, why not? Because I can't express pi as a fraction in its purest integer sense. Okay, I'm going to sort of squeak out a definition in what I'm saying here. You're going to have to come up with definitions on your own. However, here's somewhat of a working definition. An irrational number is a number that cannot be expressed as a, check this out, as a ratio between two whole numbers, or integers even. So I can't express pi as a fraction. You remember in middle school, don't write this down, remember in middle school where you were learning about pi and the circumference of a circle and all this stuff, and then you had to do these calculations and they would say, use pi equals 22/7. It made me so mad. Well, it didn't make me mad in middle school, but then as a math teacher it makes me mad when I see that. First of all, pi does not equal 22/7. Pi equals 3.141592635388462643383462643383 I think. But pi is equal to this never-ending, never-repeating decimal that has no pattern whatsoever. But this is a nice, pretty fraction that actually is a repeating decimal. It's 3.14 and something that's not exactly the same. So what they should say actually is use pi as approximately this. Because these are not the same. They are not. This is close, but it's not the same. So pi cannot be expressed as a ratio between two integers or whole numbers. Okay, story time. Ancient Greece, there was a society of mathematicians, well, mathematicians, I think scientists, you know, studying stuff, general knowledge seekers, very intelligent individuals, a little crazy though. They were a little irrational, bad joke, but they discovered irrational numbers. As odd as that sounds, they discovered that irrational numbers exist. Let me give you an example of something that happened. And true story, somebody died over this, okay? Because they thought that nature was just perfect in its numerical sense. I'll explain that in a minute. Let's suppose you have a square, and this square is 1 foot on a side. So 1 foot, 1 foot. Now they didn't use feet to measure things back then. I don't know what they used, but it wasn't feet. But 1 foot every side, all the way around, and it's square. And they had this brilliant question. They said, well, how long is the diagonal? So if I wanted to go from here to here, how long would that be? Well, using their own Pythagorean theorem, they can easily find it, and we mathematically would represent it like this. Well, they had this uncanny idea, this weird notion, that the only numbers that really existed were numbers that could be expressed rationally. That was it. That's all they thought existed. And so they thought that this would be something like, I'm making up a number, but they thought it would be something like 7/5, which actually it's somewhat close to 7/5. But they thought it's 7/5, and that's what it is. because we can measure it off with a ruler, but actually it's not. The square root of 2 is irrational. And when they realized that this was what we consider to be the equivalent of a decimal that never repeats and has no pattern whatsoever, then somebody died over it, because it was a heavily guarded secret, if I'm getting my history correct on that. Somebody died over that number right there. I like math, but don't kill me over it. Anyway, irrational numbers cannot be expressed as a fraction between two integers, whereas rational numbers can. So let's come back to this idea for just a second. Let me erase my doodling up here. I said these can't be represented as a fraction, and these can. And you're probably like, well, that's fantastic, but -2 is not a fraction. Oh, but wait, there's more. If you order now, we'll divide by 1. And sure enough, it's a fraction. It's a fraction. It's a fraction. So you can put them over 1, and it's a fraction. Now, in all fairness, you might say, well, I'll just put that over 1. Well, that's great, but you still have 3.141592653, all that over 1. That's not fair. We can't do that. So there we go. We have two different categories. We have rational numbers and irrational numbers, and all of them exist. So they're real. Now you're probably thinking, exist as opposed to what? Numbers that don't exist? We'll talk about it. That's a confusing question. But real numbers, let me give you some examples of real numbers. Real numbers can be anything we've talked about so far. So pi is a real number. 1/2 is a real number. 0 is a real number. Now it's hard to point at it and say, look, I have 0 of those because you can't see them. But yeah, that's a real number. -1/3 is a real number. -4 is a real number. There's some good solid examples right there. So all those are real numbers. And real numbers contain both rational and irrational numbers. And rational numbers contain integers, whole numbers, and natural numbers. Okay, well, over the course of time, our mathematical understanding increased, and we came across a really bizarre thing that we didn't know how to solve, and it was this. I don't know if you've seen this before. You don't have to write this part down. We'll continue our chart in a second. I'm just going to use some blank space to talk. Blank times blank gives me 9. What is it? Oh, by the way, they have to be the same thing. Has to be the same thing. So what would you say? Well, it's 3. Oh, that's easy. 3 times 3 gives me 9. This is easy. Let's do another one. Blank times blank gives me 16. You know what it is, right? And they have to be the same thing. You can say 4. Actually, you could also say, let's be fair, you could say -4. You could have said -3 up here. Nevertheless, what you just found was the square root of 9. So I can say the square root of 9 is 3, or -3. I could say the square root of 16 is 4, plus or minus 4. Okay, that's easy. Well, now let's mix things up a little bit. We have a problem. We're about to have a problem. A math problem. Blank times blank gives me -16. I need two numbers that are exactly the same that'll go in this blank and multiply to give me -16. What am I going to do? Because if I'm going to multiply and get a negative, then I have opposite signs. And so you might be tempted to say 4 and 4, and that's fantastic, but that's wrong, actually. That doesn't work. Because one of them has to be negative, but I told you they have to be the same thing. And so all of a sudden, this entire branch of mathematics opened up where we said, I have no idea what this is. And we don't even know how to look at it or count it. I can see half of something. I can see pi, actually. I can see something round and visualize the distance, but how do I visualize that? And somebody erroneously said, that doesn't exist. Ooh, it doesn't exist, so they called it imaginary. Now, I wish they wouldn't have called it imaginary, because now high school students think that it doesn't exist. There is a formula, and I don't know it off the top of my head. There is a formula that is used in electrical currents that has an imaginary component in it, and it'll shock the fire out of you. So it exists. Imaginary numbers exist, but they are called imaginary numbers. So let me branch over here. That was my spiel on why you should believe in imaginary numbers, even though they're called imaginary numbers. Imaginary numbers. Okay. Now, within that, I'm going to give you one quick definition. You might have seen this before. The square root of negative 1, well, and that goes back to our little quandary we had a minute ago. Quandary is something that's hard to solve. So something times itself gives me negative 1. That doesn't quite compute to me in my finite mind. And so therefore, the square root of negative 1 is an imaginary number. All right? Well, that is also called I for imaginary. And so if I wanted to, I could multiply it by, I don't know, 4. I'm making that number up. So 4i is imaginary. Let me give you a couple other examples of things that are imaginary. Negative 1/2 I is imaginary. All right, let's branch out a little bit. 6 plus 2i is imaginary. What this really means is, and I'm going to write this one down, you don't have to, but this really means 6 plus 2 times the square root of negative 1 is imaginary. So, I can do a couple more. So we're going to do one more. 5 minus I is imaginary. Okay. So, notice every single thing we had here had a I component to it. I'm going to erase this part right here because it's driving me crazy. Notice everything you see here had an I, and everything you see here does not. Whew! Okay. You ready for one more? Told you this was going to fill up your paper. Complex numbers. That's it. That's the whole shebang right there. Complex numbers can be real, they can be imaginary. Complex numbers, if they are real, could be rational or irrational. If they're rational, they could be integers, whole numbers, natural numbers. If I wanted to list examples of complex numbers, I can put anything in here in this category. I'm going to. 1/2, that's complex. That doesn't look complex to me. Oh, it's not too complex, but it's considered a complex number. 0 is a complex number. 3 times the square root of negative 1 is a complex number. Negative 4 is a complex number. Pi is a complex number. Can I throw something at you and I hope it sticks? If it's a post-it note, it will. Ha, bad joke. E is a complex number. In case you care. E is irrational. E is 2.718281828. It doesn't keep repeating, but it's a number. It's like pi. It goes on forever. Square root of 5 is a complex number. Now, if I wanted to, I can try to categorize all these. And real quick, I'm going to, and then I'm going to tell you which definitions we're going to find, and then you're on your own. So, complex numbers, that would be like 1/2. Well, 1/2, is it imaginary? No, it doesn't have an I. Is it real? Yeah, it's real. Is it rational or irrational? Hey, it's a fraction between two integers, so it's rational. Is it an integer? No. Okay, so if I'm categorizing each of these, I would say this is complex, real, and rational. Okay, let's go to 0. 0 is complex. Is it imaginary? No, it doesn't have an I. Is it real? Yeah. It's rational. It's an integer. It's a whole number. It's not natural, though. 3i. Is it real or imaginary? Oop, that one's obvious. It's over here. Okay, negative 4. Negative 4 is clearly complex. It is a real number. Is it rational? Yes, it is. Negative 4 divided by 1 is a fraction. That's a real good fraction I can deal with and call it a rational number. Negative 4 is an integer. See, negative 4 is right over here. Whole number? Nope, not so much. Pi, boom, obvious. E, obvious. Square root of 5, obvious. One more. Square root of 9, where does it go? Oops, square root of 9. Square root of 9, does it go here? No. What is the square root of 9? Square root of 9 is 3, assuming we take the positive and not the negative 3. Square root of 9 is, treating it as just positive 3, would be a real number that is rational. It's an integer, it's a whole number, and it's a natural number because there it is right there. Square root of 9 is 3. Okay, here's your assignment. On the back of this paper or another piece of paper, you need to, as part of these notes, write definitions for each of these. They don't have to be elaborate, but they need to be as concise as possible. You can use examples, but don't make an example like, don't give a definition like, natural numbers are numbers like 1, 2, 3, 4. Well, that's lame. I already told you that. So give me something like natural numbers are counting numbers, starting with 1. You could do that. Okay? There, I gave you your first definition. So you need to find a definition for that one, for that one, for that one, for that one, that one, that one, that one, and that one. All of the ones that we have, all of the different types of numbers in the number system, all of those need to have a definition for them. There you go.